And welcome Calculus 2 students. We are going over the divergence test first up. With this test we're going to look at some series and we're going to decide whether or not it diverges. We do this because finding the convergence value is sometimes difficult. So first off we want to eliminate those series that diverge before we go and try to figure out what they might converge to. So if we can find that it diverges, we're just done. Now, for a series to converge, that means its last term has to be equal to 0, or when I get to that infinite term, that value is 0. Therefore, if that last term is not equal to 0, if the limit of that is not equal to 0, then we know this thing is diverging. So let's look at this guy here, and we're going to look at the limit of this thing as k goes to infinity for this k over k plus 1, because we're going to look at that last term. We see that this thing goes to 1. Since it's going to 1, it's not going to 0, therefore it diverges. And the next one, I'm going to do the same thing. I'm going to go ahead and bust that apart. Limit as k goes to infinity and to 1 over 2 to the k plus 3 over 2 to the k. I see that this guy right here, this is going to get bigger and bigger, so this term is going to 0. This term, however, because this is over a 1, this term is actually going to infinity, which means this is not equal to 0, therefore it diverges. It's always nice. The next one, limit as k goes to infinity of 1 over k, well this one definitely is 0. Therefore, it doesn't diverge. That's all I know. I know that it's could converge. And I know that it does not diverge. That's all I know from this one. This one, well, it's about like they're asking me the same thing but a little more extreme. 1 over k squared. This limit is of course 0. And this one could converge. Oops. Converge. What I know for sure is it definitely does not diverge. Now we looked at this one. We looked at this series in our previous example, and we said that it could converge. However, our harmonic series theorem tells us that this thing diverges even though the terms go to 0. We see that the sum of these terms, that sum keeps getting larger and larger and is not going to any particular value. And the reason for this is the sum of the areas of the rectangles is greater than the area under the curve of y equals 1 over x from x equal 1 to x equal n plus 1. So because of that, this thing is going to keep on getting larger and larger, and this one diverges. So we have a separate theorem. If we can put it in a harmonic series form, we can say that it diverges, and we won't have to do anything with that problem. This next theorem involves the integral test, and this is once again a theorem that lets me know whether or not my series diverges or whether it might converge. So in this case it will tell me that it converges. Now the value of our integral that we're going to look at doesn't necessarily mean that our series converges to that point. It just, if it converges to something, some value, then we know that the series converges. We do this, so this proof is accomplished by comparing our function, the integral of our function, to either of these two series where the a sub k and the f of x are the same function, 1 over x and 1 of k, or the same, they go by the same values. And I'm going to go through this particular series. I'm going to look at its function by that same. Notice how the function itself includes all of all of the area under the curve. And the series has little parts either out of it or above it. So therefore, if either of these two, or if this function converges, then I know that either of these two would also converge. So let's go ahead and look at that integral. Now, after performing this integration, I get that the integral value is infinity. This means that if the integral diverges, then the series diverges by the integral test. Now, I will make note of the fact that I should be checking to see if my function that I am representing my series with is continuous, positive, and decreasing. And I could look at a few of the terms, but how I would really know for sure is I could perform the first derivative test and show that it was a decreasing function. And that would be probably what I would need to do if I was wanting to prove it for sure. But even if that would be, seeing as this integral diverges, it was kind of like I didn't really need to do it anyway. But if I was wanting to say for sure that it converged, I would probably need to show that here I have a continuous, positive, and decreasing function, and its integral is some value that goes to some constant, therefore it converges. So I would probably need to show that if it did something other than diverge. Alright, so here we are, we're going to play again. We have example B. I am going to look at this as the integral from 3 to infinity of 1 over square root 2x minus 5. I'm going to perform this integration, and I'll do this with a u substitution. I'll just let u equal that 2x minus 5, therefore I'm just off by that factor of 2. Alright, after completing this integration, I find that this guy diverges as well. Since he diverges, no point in proving that he's continuous, positive, and decreasing to say that he converges. So I'll just move on. For the next one, I would need to note and prove that the series was positive and decreasing, and then I would use the integral test, and this integral test looks like this: dx over x squared plus 4. And then, since I have these limits of integration that involve infinity, I'll use that limit and perform that integration. Because this integral has a finite value, that means that this infinite series converges. So it converges. I don't know what it converges to. It might or might not be pi over 4, but I know that it definitely converges because it is continuous, positive, and decreasing. In my next theorem, I'm going to look at series of this form where p is my exponent. I could say that this p here would be to the 3/4 power. So note that since I have a p series, I can say that it converges when p is greater than 1. Nope. And it diverges when p is less than 1, so this one diverges. This one is not exactly what I wanted it to be, but I could rewrite it and make it look like k equals 3 to infinity of 1 over k squared, meaning that this is 1 over 3 squared plus 1 over 4 squared plus blah blah blah. In this one, my p equals 2, and that would mean my p is greater than 1. Therefore, this guy converges. In this next one, we are looking at a p series, and We need, in order to use this theorem, because we're going to be using the remainder and finding exact values of the series, we need to make sure that we have a continuous positive and decreasing function, and we do have that. We are asking for how many terms of the series must be summed so that we are within 10 to the negative 3 or 0.001 of the exact value of the series, so that has to do with the remainder. So I'm going to look at my remainder formula here, and I see that I've got to have this within, and this d over x squared is my function that follows that 1 over k squared series. When I integrate this thing, I will get 1 over n. I know that at this point this 1 over n must be less than or equal to 0.001. That means that n has got to be greater than 1,000. So I need at least 1,000 terms of the series to make sure that the remainder is less than 0.001. Looking at my formula for how the sequence is bounded, I see that my sequence is bounded, and here is my sequence here in the middle, by this sum of my 50 terms, in which I got off the calculator, plus this integration of both the left-hand side and the right-hand side, or the upper and the lower of this sum. So what you're going to end up with when you integrate this, and I'll go ahead and I'll get what this guy is right here, and then we'll get what this guy is right here integration wise, and then we will figure out what my sum is, because my sum is going to be in between this s of n plus my integration here to here of my function, and it's going to be bounded on the bottom by this sum plus the next term, n plus 1 of f of x dx. So when I integrate this 1 over k squared, what I'm going to end up with on this right hand side is 1 over n, and on this left hand side I'm going to get my sum plus 1 over n plus 1. So I'll just do that computation, and what I'll end up with is 1.64471 using my s sub 50, because I'm using the 50 terms, which would then go right here. It's in between s, and if I get 1.645133, if I just take the average of these, I'll get that my sum is about equal to 1.644937. In this next example, we're going to use properties of convergent series, which allows me to break things apart and find my sums that way. You'll notice that since I'm going to be adding these anyway, alright, so since I'm adding all of these up here for the sum, I can just add this first series of terms up and then add up these and then subtract those two values, and I'll get what that total sum is. Alright, just looking at each of these series individually, note if I look at the terms of my first series, I have a equals 5 times 2/3, where r is 2/3. I know that as long as r is less than 1, and it is, I can say that the sum of this series is 5 2/3 over 1 minus 2/3, and get that computation. Same here, wrote out this series, found my a and my r, noted that my r is less than 1, so I'll get that sum. Then when I get finished, I'll just get to add them together. Alright, so my total sum is then just going to be 10 minus the 1/5, because it's the first one minus the second one, using my properties for that, then I will get this is just 49/5. And that concludes this section. If you have any questions, you know where to find me. Email me or see me at the Collaborate.